Is this plug? Yes. Okay, perfect.
So good morning, and thank you very much for your patience, because we had some technical troubles with introducing our presentation, so hopefully all of these troubles are solved. So I can welcome you here at another of our seminars, which is sort of special, as you can see even from the number of people in the audience, because today we have a guest who has been borrowed from the Institute of Geophysics, who is visiting the Institute of Geophysics this month, and it is Christophe Sotin from JPL in Pasadena, in California, in the United States. I know a person who knows the guest much better than I do, so I will give the word to Clara Holešovičkách from the Institute of Geophysics, so that she can tell us a few more details about our today's speaker. So please.
Thanks, thanks everyone for coming. It's a great pleasure to introduce Christophe, who has been my postdoc supervisor during my time at Jet Propulsion Lab. And since that time we keep working together, and Christophe keeps coming to Prague to visit our department. So now he's spending 1 month of his research leave at our department working on different projects. And Christophe graduated from geological engineering and geophysics from the University in Nancy, and obtained his PhD in Paris at Institut de Physique du Globe. He then moved to Brown University in Rhode Island, Providence, to work with Marc Parmentier on the dynamics of the mantle of the Earth. And upon coming back to France, he started lab in planetary geology and geoscience in Nantes, his native city. And then he moved back to US, to California, to work at the Jet Propulsion Lab, where he now works as a chief scientist for the solar system exploration. Christophe works on a broad area of topics, including geophysics of the interior of the bodies, dynamics of the mantles of terrestrial planets, as well as icy satellites. He also contributes to research in atmospheric sciences, including Venus and Titan, the largest moon of Saturn, which will be partly the topic of this talk. And Christophe also participated in many missions, and just to mention one is the Cassini-Huygens mission, where he was a member or scientific member of the visual and infrared mapping spectrometer, and he was responsible for planning the observations of Titan, the moon of Saturn. And in today's talk, he will introduce or present some of the most important discoveries of Cassini mission.
Well, thanks, Clara. Thanks a lot for the invitation, for the introduction. It's great to be here. As you know, so I am French. I have been in the US for the Jet Propulsion Lab for 13 years now, and I am part, as Clara mentioned, I am part of the Cassini-Huygens mission that was stopped about more than a year ago on September 15th, 2017, after 13 years in the Saturn system. And so it's great to be in Prague. I try to come once a year. It has been more than I think 18 months since I last came to Prague. And I work with different people. As you will see in this presentation, there are some aspects of the research, of the results that came from the lab here in Prague. The Jet Propulsion Laboratory is known for the rovers on Mars mainly, but it manages also several missions, like the Dawn mission, which visited Ceres and Vesta, like the Voyager mission, the Galileo mission. All these missions were managed by the Jet Propulsion Laboratory, and it's just fascinating for me to be in charge of the science objectives of the future missions that are being built at the Jet Propulsion Lab. So it's very exciting work. And today, so JPL was also managing the Cassini-Huygens mission. It's a huge mission. I am pretty sure that in 100 years from now, we will find out that this Cassini-Huygens mission was the largest mission that was done at the end of the 20th century, beginning of the 21st century. Yeah. It has just been an incredible mission. So there will be a bias, I guess, in the main discoveries, because my background is in geology, geophysics. I am interested in the moons and in the satellites, but I will also speak about Saturn. But of course, I am more interested in surface processes, interior processes, than atmospheric processes in Saturn atmosphere. Okay, so just to, I'm sure you know that, but just to make sure, the size is good, the distance is not. I guess everyone figures that out. So the solar system, you have the 4 inner planets, Mercury, Venus, Earth, and Mars. You have the asteroid belt in between, the inner planets and the outer planets. And then you have the giant planets, Jupiter, the largest one, then Saturn, and the icy giants, Uranus and Neptune. You can say, well, where is Pluto? Well, Pluto is here, so somewhere here. Now it's a dwarf planet. It's a new category, and you have several dwarf planets, including Ceres, which is the largest asteroid in the asteroid belt. Anyway, so I'm going to speak about Saturn, which is at about 10 astronomical units from the Sun. Which means, just to think about the energy which is necessary, the Earth is 1 astronomical unit, being 10 times further away. It means that it receives 100 times less sun from the power from the sun. So it's something you have to keep in mind in terms of why we don't use solar panels, for example, to go to Saturn. It's just you would need a very, very large solar panels in order to be able to get the energy, the power that you need for the instruments. So the Cassini-Huygens mission, oh, sorry, no, I have another slide just to give the dimension of Saturn. So, of course, this is not Saturn. This is the Earth, and this is the Moon. But if Saturn was to come closest to Earth, this is, it would occupy mostly the distance between the Earth and the Moon. So it's about 300,000 kilometers. You have, obviously, Saturn here, and the rings, well, the most visible rings around Saturn. So it gives you an idea of the object, and just think that Cassini was in this environment during 13 years. So the Cassini mission was decided after the first observations by Voyager in the early 80s. So the project actually started at the end of the 80s. I wrote my proposal in 88. I'm saying that, for the young people. 88. So it was 30 years ago. So it's a big chunk of my career to have been on the Cassini mission. So at the time I wrote the proposal, I did not realize that it would be important for the remaining of my career, of my life. Cassini-Huygens, you have the Cassini spacecraft here, and on the Cassini spacecraft, the European Space Agency built a probe that landed on Titan, and this probe was put on the Cassini spacecraft. So it was a cooperation between the European Space Agency and NASA, the US Space Agency. And actually, it saves the mission. That's also something you have to keep in mind, because in the US system is very dynamic, and the president can cancel a mission anytime. So actually, the president of the United States in the mid-90s decided to cancel all the big planetary missions because they were too expensive, and he wanted to do something else with the money. But because Cassini had a very strong involvement with Europe, it saved the mission because there were some agreements with a foreign partner. So, for example, the Craft mission was cancelled. It was about the same size as Cassini, but it didn't happen. So it's good, to do international partnership. Somehow it helps get the mission go through a long period of time. When I told you about Cassini, 30 years, it's you have to maintain the pressure and to work during all these years. So here are the list of the countries. I think it's about 27 countries. And including Czech Republic, because Czech Republic is part of the European Space Agency. So all the data, of course, are accessible for all these countries, and actually they can be accessed by any person in the world. Okay, so this is something I remember because I was at the launch pad when Cassini was launched and went to Saturn. And by the way, it was supposed to be launched on a Sunday evening, the night of Sunday to Monday, and just 1 minute before the time, they decided to stop the launch because the wind was blowing in the wrong direction. And if something happened on Cassini, then there may be some material falling on the population. But 2 days later, it was also during the night, there was this launch, a beautiful launch. There was a cloud just well positioned in order to see the rocket, and then the rocket flew. And I have exactly the same pictures. And so this happened in '97, so it's more than 20 years ago, 22 years ago. And so you have also to keep in mind that the instruments that were built and which are on Cassini were built with the technology of the early 90s. So of course, some of you were not born in the early 90s, but you can see that the technology has made incredible progress between the early 90s and now. So it's very different. We would do much smaller camera. We would do much better instruments, but you have to decide at some point, well, it's time to go. But it's, you will see that the data are just amazing. Okay, so now Cassini, this is a trajectory. A lot of stories about the trajectory, but I won't go into the details. So it did some flyby of Venus in order to get a gravity assist and to be able to get faster to Saturn. It arrived at Saturn in 2004, you can see here, and the nominal mission was 4 years, but there was already an agreement to extend it for another 2 years. So between 2004 and 2010, we call that the equinox mission because the equinox, so spring on Saturn, was at the end of 2009, so that was the equinox mission. And then in 2009, we wrote a proposal in order to have more time in the Saturn environment for reasons I will describe later. Just the results of Cassini were so amazing that we decided to spend more time we decided, and we successfully convinced NASA that we can spend some more time in Cassini. And then at some point we had to stop, so we decided to stop in 2017. Actually, there was no more propellant. According to the gauge, there was no more propellant in the spacecraft, but apparently we could have lasted some more time. So Cassini ended into Saturn's atmosphere on September 15, 2017. So it's about 13 years. 1 year on Saturn is about 30 years. So it's about 6 months, or I would say half a year, that we spent in the Saturn environment. Okay, so what did we do? This is a list of orbits around Saturn. So I think it's about 160, I don't remember the exact number. We had, among these orbits around Saturn, 127 times we used Titan. Actually, Titan is at about 1 million kilometers from Saturn, and it's a big satellite, so it was used as gravity assist in order to change the orbit of the Cassini spacecraft. So you can see that at the beginning, of course, we were in an equatorial orbit, and then just by using a little bit of propellant and adjusting the thrusters and using Titan, then we could visit Europa or Dione, or the rings, just move into the Saturn system. We also change the orbit, going from equatorial to polar orbits, which was obviously interesting to look at the North Pole of Saturn and get views of the rings from above or from beneath. And then we did some other equatorial orbits and then some new polar orbits, etc. We were playing in the Saturn system, with using Titan as a gravity assist in order to visit the different bodies according to the discoveries that were made. Something that we were supposed to do at the beginning of the mission is to visit one of these satellites, small satellite, Enceladus. And because of the discoveries at Enceladus, then we had many more flybys of Enceladus, as you can see here. Altogether, we did 23 flybys of Enceladus at the beginning of the mission, not knowing what was the activity on Enceladus. We had only 3 here. And then we had icy satellites flyby, 15 altogether. As I mentioned before, by using Titan, we were able to visit some of the other small satellites of Saturn. And here is the season. So we arrive winter. As I mentioned before, we went through the equinox. So we had spring, and then we ended the mission. It was summer for Saturn. So we could see the seasonal effect on the different bodies. Oops. Okay, so this is, I will start with Saturn and the North Pole of Saturn. And there is one structure, maybe it's not here that we see it better. There's this structure here. You can see the North, so this is the North Pole. You have the vortex here. And you have this hexagonal structure that was observed by Voyager 30 years before. So it's very stable, and that was one of the first surprises of the Cassini mission, is that the atmospheric dynamics on Saturn is very, very stable. You have some big storms that you can see here. By the way, the scale here is about 80,000 kilometers, so it's really a huge structure. And I read the paper, so it's not my field, but I read the papers. I couldn't find the papers that gives an explanation for this hexagonal structure in the atmosphere of Saturn. With the different instruments on board, in addition to the cameras, we had some spectrometers. So they took images. Actually, this is a false color image of the North Pole of Saturn. And by taking these images, they were able to get into the center of the vortex. So this is emission. This is at 5 microns, so the red is at 5 microns, so it's a emission coming out from Saturn, and so you can get information about how much heat is being emitted by Saturn in this case. So this is the vortex, so the vortex is actually downwelling, but you can see that close around the vortex, you have these storms, and you have these clouds, which apparently for the people doing atmospheric dynamics were quite surprising. There was a paper by Kevin Benz you can see it's a recent paper, 2018. Actually, they used some of the data from the last flybys of Saturn. And what they find, so this is a vortex, so it's very dark because there is no structure, it's a downwelling. But on the edge of the vortex, this number 2 here, this is ammonia cloud that were observed very close to the vortex. And right now, there is no model that can explain how you get some upwelling in order to create these clouds, these ammonia clouds, so close to the polar vortex of Saturn. You have some other clouds you can see here. The number 1 is also an ammonia cloud, and ammonia actually is well detected in this band at 3.07 micron, which is the blue line which is represented here. And you can see that by using the infrared spectrometer between 1 micron and 5 micron, you can get information on different components. pH3 is mentioned here, but there are other components. H2O, obviously, it's at 2.6 micron. And the fact that you don't have any signal here is because there is absorption by H2O. So there are a lot of components that can be observed by the infrared camera. So dynamics is still a mystery. We got some additional data, in particular from the rings. So I will mention that a little bit later. So the rings, you can see the color. So we have, they are named in order of discovery. It will come back if G is here. Okay, so if we go back, you will see the E ring, the B ring, C ring, which is here. There is a D ring, just even closer. E ring, which is actually populated by, now we know by Enceladus. Enceladus is ejecting material in space, and this is populating the E ring. And then you have the F and G ring. Okay, at the end of the mission, when Cassini was going into Saturn, actually what was decided was to go in between the F ring, the D ring and Saturn. And you will see that it was kind of a challenge because, well, first we didn't know exactly what was in between Saturn and the D-ring. So people were wondering whether you don't have big rocks and that would damage the spacecraft. And what we found out is that it's incredibly empty. There is nothing. I mean, even the people who were collecting dust, you know, they were hoping to get a lot of dust. They didn't get so much material, just a few impacts on the spacecraft. So obviously, you know, gravity is doing its job and just removing everything in between the D-ring and Saturn. So the rings, you know, we call them the navigators. You know, the engineers at JPL who do the navigation of the Cassini spacecraft, we call them navigators. And at the beginning of the mission, people were really afraid, so they say, well, we cannot go closer to 300 kilometers from this body or from the rings. At the end, they were just flying at a few kilometers from the rings, for example. You know, they were just, it was so precise in terms of the location of the Cassini spacecraft that they could get very close and get amazing images. So in that case, it was over the B-ring. This is, here you have the outer edge of the B-ring. You can see that it's very well marked. There is nothing outside. The fact that there is nothing is because there are some resonances going on between the rings and the satellites, as I will show later. But the sun, in that case, was coming along the rings, and so the shadow allowed the people to get the topography of the outer edge of the B-ring. So in addition to be able to determine the density or the number of particles per square meters, they were also able to get some ideas, and you have this topography is a few kilometers. So actually there is also some variations of a few kilometers at the outer edge of the B-ring and actually at the other rings. In these rings, that was unexpected. You know, when you build a mission, you have some science objectives. This science objective was not put into the objectives of the Cassini mission. We did some stellar occultations through the rings, and what was discovered is that there were some kind of resonance. You can see the pixel. Sorry, I have to explain. You have 0, which would be, let's say, Saturn, so the 1 bar limit. And then you have the rings going to the left. So you are at different distances from Saturn. And what you can see, you can see the radius minus the radius of Saturn. And what you can see is that you have this kind of holes or spirals in the rings. And when that was discovered, people were wondering, what is that? Why do we have this kind of spirals in the rings? And apparently, well, the interpretation that we have now, it was a paper by Matt Edman, and he, oops. Oh, okay, I'm going much too fast. Okay. Matt Edman, his first paper was in 2013. The interpretation is that these gravity effects are excited by the normal modes in Saturn. So by looking at this effect, at these spirals, at the distance between the different peaks, then you have some information about the normal modes of Saturn, which in return give you information on the interior structure of Saturn. And the conclusion of, one conclusion of his study, I think it was his paper in 2016, is that there must be an abrupt a change in density inside Saturn, something you're going from 1 gram per cubic centimeters to 3 grams per cubic centimeters at a radius of about 10,000 kilometers inside Saturn. So just you know, by seeing this gravity effects in the rings. It's kind of, you know, it's used what we call, it's chronoseismology. It's a kind of seismology. You know, you see the normal modes of the planet affecting the structure of the rings. Okay, inside the rings, you have the small satellites. So you have several of them. And again, because we're able to fly very close, so you can see the scale here, it's 10 kilometers. So this is a few tenths of kilometers. And it was very surprising to see this kind of skirt, you know, around this very small satellite. And not only it seems very thin, but here you can see there is an impact crater. So there is some structure, and it's still solid. And in order to maintain that, of course, it's gravity, but it's not, because we see this impact crater, you can see that it's pretty solid. You know, it's not something which is just floating around and, you know, dust floating around. It's really something solid. Then we observed the birth of a moon, a small moon. It was nicknamed Peggy. So we saw the moon forming, and then the moon migrated outside the rings. By the way, this is the E-ring, and this is Enceladus. So you can see the connection between Enceladus and the E-ring. So it was, you know, witnessing the formation of a new moon was interesting, and then people started to think about what if the small satellites of Saturn were in fact created from the rings, and I will come to that. So before I do that, what are these small satellites? So you have the rings I mentioned before, and then you have these small satellites: Mimas, Enceladus, the E-ring here, Tethys, Dione, Rhea, and after Rhea you have Titan, which is the big one at more than 1 million kilometers. And then you have Hyperion, which is a small rock, Iapetus, and Phoebe. We didn't see much of Phoebe and Hyperion because, as I said before, we use Titan as a gravity assist. So we just got a possibility to see these bodies when we arrive at Saturn. We did one additional flyby of Iapetus later during the mission, but it cost a lot of propellant, and so it was decided to not go too much to Iapetus since we discovered much more interesting things at Enceladus. So an idea came out that maybe, you know, Mimas, Enceladus, Tethys, and Dione could have formed when the ring was more massive. At the end of the mission, we were able to determine the mass of the ring, and actually the mass of the ring altogether, it's about half the mass of Mimas. So it's not a lot. What remains in the ring, if this hypothesis is right, what remains in the rings is not a lot of mass compared to the mass of these small bodies. So this is, you know, the study. So what is here? You have the semi-major axis, so the distance from Saturn. It's in radius of Saturn, so from 2 radius to 8 radius of Saturn. And here you have the location of these 5 small satellites. Enceladus, for example, is 250 kilometers. No, I'm correct on that. 250 kilometers, yes, in radius. And so this is their location right now. And depending on how the heat can be dissipated into Saturn, which depends on the factor that we call the quality factor, then you can try to trace back the location, the distance between the moons and Saturn. And if you use a constant value of this quality factor, what you find out is that actually the moon should have come from the rings much earlier or much later than the origin of the solar system. So this is time. So here it's 4.5 billion years. This is the age of the solar system. This is the age of Saturn. We think Saturn formed at that time. And so you can see that in this model, well, the small moons would be much more recent than what we thought. You know, before getting to Saturn, we thought that it was 4.5 billion years. And so there was a similar paper by Huygens and Nesvorny in 2016 about the late formation of these moons. There was a previous paper by Sébastien Charnoz, but it was not as detailed as the one by Chuk et al. And then this picture actually comes from this figure comes from a paper by Fuller et al. In 2016. Now people are refining the models, but I think that's a really big discovery of the Cassini mission from the data to find out that the moons could be could have formed much more recently than what we thought. So now I'm going to move to one of these moons, Enceladus. So this is Enceladus. You can see the fractures. You can see that there are some terrains which are without any impact craters, some other with more impact craters. And at the first flyby of Enceladus, what was observed is unusual comet-like magnetic field which was detected. So there was some deformation of the magnetic lines, and then so there was something going on Enceladus that we did not understand. And then it was decided, so because there was this signal, it was decided to get closer to Enceladus because we're thinking maybe there is a kind of induced magnetic field in Enceladus. So the PI of the magnetometers on board the Cassini spacecraft is Michelle Dougherty from the UK, and so she was able to get a flyby at 175 kilometers. And during that flyby, what we found out is that actually there are jets coming out of Enceladus. That was a big discovery because small moon, 250 kilometers, temperature minus 200 degrees. So it's very, very cold. So everyone was expecting a ball of ice, nothing else. And then you get to Enceladus and you see these geysers coming out. So first interpretation say, well, maybe it's like a comet, but very quickly what we found out first by looking in the UV, so we were able to see also this plume, the geysers. What we found out is that actually the plumes were coming out of these faults. So there are 4 faults on Enceladus. This is one of them. They are about 130 kilometers long. This is 2 kilometers wide. It's deep. Here it's written 500 meters deep. I guess it depends where you are. And then you also have this wall around the fault. But what is really impressive is that you have this, the geysers that come out. And then there was a paper by looking at the intensity of the plume. The paper found out that there is a correlation between the intensity of the plume, so the amount of material that comes out of Enceladus, with the mean anomaly, so the distance between Enceladus and Saturn. And the faults that you see here, they close and they open, they close and they open, and when they open, there is more material coming out than when they are closed. So it was another paper by Matt Edman that made this discovery, and then there were more papers with more observations, but it was decided to study Enceladus in much more details. One instrument is a thermal infrared, and here you have the faults, the 4 faults I was mentioning before, and it's clear that you have much more heat coming out of this fault than in the background. So obviously it's hot. Well, hot. It's still ice, so it's not, it's not Venus here. We are still close to 0 degrees. But you can measure the heat flux which comes out of these faults, and it's very, very large. So what is a source of energy? What can give so much energy to small bodies? And the answer is tides, tidal dissipation. So because Enceladus has its distance to Saturn that varies during its orbit, it can produce some power. But we had some very hard time to find out how much power is needed. Another observation, which was very surprising, is that actually there is a global ocean on Enceladus. So again, 250 kilometers, and below about 20 kilometers, there is a 40-kilometer ocean. And this ocean has been discovered because there is a decoupling, there is librations on Enceladus. So there is a decoupling between the crust here and the rocky core which is inside. And the best way to explain the decoupling is to have a global ocean on Enceladus. So people here in the lab have been working and have published this map of the topography, looking at the gravity data that were acquired by Cassini, the topography data also acquired. They were able to determine how much heat is being produced just at the base of the icy crust. And they were also able to determine what is the thickness of this icy crust. It's great work. I think the paper came out in 2018. I hope I am not wrong, but I think it's 2018. Andrej? Yeah. Yes? And it was a collaboration with people at the University of Nantes who are working with the lab here in Prague. And so the people in Nantes have developed a model for the circulation inside Enceladus core. And what they were able to find is that actually you can produce a lot of dissipation by the deformation of the rocky core if it's a porous core. And you can get the total amount of energy that you need. And 30 gigawatt doesn't seem like a lot of energy. Just to give you an idea, if I put that into heat flux, that gives about 60 milliwatt per square meters. And on Earth, the mean heat flux is 75 milliwatt per square meters. So we have a lot of heat which comes out of Enceladus, something which is equivalent to what we have on Earth. These are some structure of the flows in the rocky core, and you have, depending on different parameters that I won't go into the details. This is homogeneous tidal dissipation. This is non-homogeneous tidal dissipation. You get different pattern. But it was also a great collaboration between two laboratories. In addition to the gravity, the geophysics, you can do also some chemistry. So on Cassini, we have a mass spectrometer, and because Enceladus is just putting the ocean into space, then you can collect some pieces of the ocean. So they collected the frozen ocean, and they determined, they found out that there is some silica in the ice grains. And so by looking at the amount of silica, the concentration of silica in the ice grain, and looking at the temperature, you can find what is the pH of the ocean. So it's just incredible to determine the pH of an extraterrestrial ocean just by doing this kind of measurements. Again, totally unexpected. That's one of the reasons why the Cassini mission was extended. So the silica solubility is in this range, and you can see that it constrains very much the pH of the ocean. Yeah, I forgot to mention that was a cosmic dust analyzer. In addition, they found potassium and sodium, and when you do the ratio of potassium and sodium, you get also information on the pH and the redox of the ocean, and it gives about the same answer. Well, with that, you have a rocky core, you have heat, you have water. Of course, the question is, what about life? We know on Earth, this is hydrothermal vent on the Earth's seafloor. We know that there are organisms, but we also know that the organisms that we find at the bottom of the sea, these organisms are some kind of evolution of organisms that live on the surface of the Earth. When you look at the DNA, when you look at the genes in this organism, we haven't found something which is different from what we know on the surface of the Earth. It's not the same organisms, but we all come from the same ancestor. Can this, the environment being quite similar on Enceladus, the question of whether there is life in this environment, of course, is worth being asked. It's a small body. I don't think that we have the same kind of gradients in terms of chemistry, in terms of pH, in terms of redox, on Enceladus that we have on the Earth. And apparently, disequilibrium is very important for life to exist. You need to have disequilibrium because life needs to have a reason to exist. So you need this disequilibrium. I am not convinced that you have this disequilibrium on Enceladus, but still having energy, having the elements, having the water, I think it's worth checking. And because Enceladus is giving us the material in space, just go there, grab the material, bring that to Earth, and look in the lab if there is some life. So these are potential missions that we are working on for maybe 10 years from now to bring back samples and see whether in this ocean of Enceladus life may have emerged. Now I'm going to speak about Titan. I think I am almost good. Oh, I forgot to say that. So this is a view of Titan in front of Saturn. You can see the rings here. By the way, Titan, we didn't know much about Titan. We just knew that it has an atmosphere, but we didn't know anything about the surface of Titan before Cassini. We didn't know if it was covered by hydrocarbon liquids, whether it was solid on the surface. Actually, when we launched Cassini, the favored model for Titan was that it was covered by hydrocarbons, so liquids on the surface. And when the European Space Agency built the Huygens probe, they built the Huygens probe not to land, but to splash in an ocean. So, of course, we found out that it landed at the end. So Titan is the only satellite which has a dense atmosphere. The pressure on the surface is 1.5 bar. The density is 4 times the density at the surface of the Earth because the temperature is much smaller. So you can compare Titan with Venus, Earth, and Mars in terms of the atmospheric density. So of course Venus has a much larger density. By the way, it's mainly nitrogen on Titan with methane. So nitrogen, like on the Earth, we don't have the CO2 like it exists on Venus. And then you can compare Titan with the other icy moons like Europa, Enceladus, or Ganymede. And this axis is increasing water-rock interaction in the bodies. And so Enceladus has clearly a lot of water-rock interaction. Europa, we don't know much about the interior of Europa, so it has to wait for future missions. And Titan would be with even less interaction with the rock for reasons I won't go into the details now. But I can answer the questions. So this was Huygens landing. Of course, this is after the landing, so we reconstructed with the images that we got from the Huygens lander. You can see the rivers or riverbeds because there is no liquids now. But Huygens so landed in this area. There were some dune fields, and the descent was just a few hours, and then we saw these pebbles at the surface of Titan, and these pebbles, you can see that they are rounded, so they have been transported by some liquids in order to have this kind of shape. And the size is a few centimeters, up to 10 centimeters for this one. And when we got the first image, we thought that we were on Mars because it's red, there are rocks. But with instruments, we found out that it was not rocks, it was not silicates, it was ice rocks covered with some organic material. But I remember, the first image that came, someone thought that they put Mars images on the screen just to wait for the images coming from Titan. Okay, just a comparison. So this is a light. So you have the pebbles. I won't go into the details. Just to also, this is the print of an astronaut shoe on the moon. No, this year is going to be the 50th anniversary of the first man on the moon. So I just give an idea. And here on the right, you have some of the river beds I mentioned before. So it shows that some liquids have run on Titan's surface during the past. And some liquids, of course, it's not liquid water because it's too cold. It's 94 Kelvin at the surface, so it has to be hydrocarbons like methane or ethane. So this is another view of Titan, and you can start to see some of the lakes, hydrocarbon lakes on Titan. And what we observe with infrared at 5 micron, what we observe is a very strong light, bright feature on the surface of Titan during one of the flyby. So it was a lot of excitement. Someone thought that we had discovered a cryovolcano on Titan, a volcanism on Titan. But then we look at the geometry, and what we found out is that this is a specular reflection. At 5 micron, the light is not scattered in Titan's atmosphere. And so we were in the right geometry above this lake. Well, it was not exactly this lake, but we were in the right geometry above a liquid surface in order to get all the brightness from all the light at 5 micron from the sun. So it was a good confirmation that there are liquids on Titan. This is one of the lakes of Titan. It's called Ligeia Mare. And with a radar instrument, not only they found that there were these lakes, but they found also the bed of the lake. So they were able to determine what is the thickness of hydrocarbons you have in the lakes. And from that, you can determine the volume of hydrocarbons, and you can start looking at the cycle of methane and ethane, or carbon in general, or organics in general on Titan. So we have now several of these profiles. Of course, again, it was not foreseen by the Cassini mission. When we started Cassini, first we didn't know that we would find lakes on Titan, and then no one imagined at that time that we would be able to determine the thickness of the lakes on Titan. It has never been put into the science objectives of the Cassini mission. So we were able to see lakes at with different instruments, including the infrared camera, which was able to see Titan's surface in 7 different windows, infrared windows. So we can see actually through Titan's atmosphere in some wavelengths because light is not scattered by the atmosphere on those wavelengths. And at the end of the mission, well, you get some kind of a geological map of Titan. So you can see that this is very recent. So Titan, this is the equator. You have the poles. You can see here the lakes on Titan. This is Kraken Mare, Ligeia Mare is here. And Titan is characterized by this equatorial band. And what is brown here means dune fields. So you have dunes on Titan. You have an equatorial band of dunes, and the sand, it's not the sand that we know on Earth, it's more organic sand. We don't know exactly what it is made of, because Huygens didn't land in a dune field. Huygens, I forgot to mention that, but Huygens landed, it's here at Erie, so on the white terrace here. Actually, Huygens landed at one of the highest points on Titan. Well, topography on Titan is not very high. It's plus or minus several hundreds of meters, maybe plus or minus 1 kilometer. But that's where Huygens landed. Oops. Yep, right here. So brown is the dunes. What is blue? We think it's water ice. And white is organics covering some of the topographic reliefs. And then you have this structure, which is very enigmatic. It's called Xanadu. It has some finer structures that I won't go into the detail, but there is a lot of geology you can do here. I say it's weird because actually Xanadu is a depression, and I don't understand why the dunes or the material, the sand, is not filling up this depression. So either the dunes were formed long ago or long before this depression formed, but there is still a lot of work to be done. By the way, this map has been obtained very recently. Actually, it was presented last week at the Lunar and Planetary Science Conference in Houston. And the geologists are now able to work with this information. But it's only at the end of the mission, when you have all the information, you can start working with all the data which have been collected. This is another work that we are actually working with Holešovičkách, we look at the correlation between the gravity signals that we have from Cassini with geology. Sorry, this is not the gravity, this is the topography. So we have the topography also from Cassini. You can see the values I told you between plus 500 meters here down to minus 400 or 500 meters at the poles. And we try to see whether there is some clear correspondence with geology. But it's really, ongoing work. There is still a lot of data which have not been analyzed by the scientists on Cassini just because we didn't have time. We had to run the instruments rather than processing the data. I was talking about the cycle, the methane and the ethane on Titan. So we know that there is methane. So methane is this CH4 molecule, but we know that methane is photodissociated into ethane pretty quickly. And if you look at the amount of methane that you have in Titan's atmosphere, it should disappear in 20 million years. So it's short in terms of geological timescales. But it's still present, and so we are trying to understand what is the source of methane. When you have ethane, what we found also is that there are clouds on the poles, so it rains ethane on the poles. The ethane is liquid, it's part of the lakes, and then the ethane can get into the ice, and it forms what we call class rates. And actually, if you have methane class rates, the ethane that percolates is going to kick out the methane from these cages, and the methane will be able to get back into the atmosphere. It does not provide a global circulation because one molecule of ethane is going to go into one site, so one molecule of ethane. So actually, you can explain 50% of the methane being recycled this way. But so we have these ethane class rates that we know on Earth, or methane class rates that we know on Earth. And it's an important part of the cycle. So you have the atmosphere, you have the liquids, the rain, the lakes, and then you have the subsurface where you have these variations. So some work we are doing with, actually during my research leave and working here with Clara is to look what happens if you put a layer of class rate on top of the ice. What happens to the ice crust? So here the ice crust is 100 kilometers, and we look at convection processes, how heat is transferred into this ice crust. If there is no class rate, what we find out is that there is a very thick cold layer on top of the convecting ice. But if you add class rates, what you find out is that the layer is much, much thinner. And the reason is that the class rate has a very low conductivity, thermal conductivity compared to water ice. It's a factor 10. So for me, it's fascinating to see. Yeah, so for something I forgot to mention is this plot on the left. This is precipitation of methane on Titan's surface, which was published by Schneider et al. In 2012. What you can see is that it rains a lot of methane on the poles, a little bit at the equator, but not that much, and it's very seasonal. Here you have it's the summer in the northern hemisphere, so actually it rains when it is the summer. It rains methane during the summer, and it rains ethane during the winter. So you have to change umbrella, I guess. But it's not a lot of rain. What I find fascinating is that the atmospheric processes are going to affect the interior processes. And somehow it's like on Earth. When you look at erosion on Earth and how erosion can transport carbonates and to the seafloor, and how subduction forms, and the role of water in subduction and in the plate tectonics on Earth. Somehow on Titan, we can see that the atmosphere is also influencing what's going on in the deep interior. Okay, so we have some good idea about Titan's interior structure. We know that there is an ocean, and we know that there is the atmosphere, the rocky core, and there are still a lot of questions that we can address actually with the data that were collected by the Cassini mission. So Iapetus, just quickly, it's kind of a funny moon. There is this mountain range, 2,000 kilometers, just at the equator. And so you have two theories. One is that it's the dust. Somehow there was a dust or a ring that collapsed onto Iapetus, like, you know, the skirt I showed to the very small moons. So that's one model, you know, that the gravity could do that. And the other one is that Iapetus shrunk during its cooling, and so by shrinking, the surface changes, diminishes, and so it can create some topography. But it's difficult to say which model is good. Okay, the grand finale. So we went into Saturn, very close to Saturn, between Saturn and the D-ring. So this is a trajectory. So, I mean, the spacecraft didn't do that. The spacecraft just go here. But the way it's represented, you have the rings in that direction, and this is the spin axis of Saturn. So it gives the impression that it did that. But it went really, really close, and it allowed us to get a very good gravity and magnetic data. So this was for the magnetic. This is the gravity data. They go up to degree 14 with the gravity data, yes. And there is some discrepancy between the observation, which are these circles, the black circles, and the models of what we call the solid Saturn, which would be Saturn without taking into account atmospheric dynamics. And so by taking into account the atmospheric dynamics, they find out that you have winds on Saturn at depths up to 8,000 kilometers. I think it's 8,800 kilometers. So actually, it's a good way to probe the winds inside Saturn. Okay, I'm getting to the end. Some of the top discoveries I mentioned. So Titan, I won't come back, but you know, the cycle, the organic cycle, an interaction between the surface, atmosphere, and the interior. The ocean present on Enceladus, Titan, but also Dione, the hydrothermal activity inside Enceladus, the role of tidal dissipation, which is important not only for Saturn, but when you think of the formation of any body in the solar system or extrasolar planets, clearly tidal dissipation is very important. The wave in the rings, providing information on Saturn's interior structure in addition to the gravity and magnetic data. And if there are people who can use all these data, so far everyone has been looking at one set of data, has not put all the data together in order to come with a uniform model for the interior structure of Saturn. Then you have the formation of the moon, which I think is really fascinating in terms of understanding also formation of planets in solar nebula. And the fact that they would be much more recent than what we know now. So what's the future? Well, there is one mission to Titan, which is in the final 2 missions of the New Frontiers program. The other mission is a comet sample return. We will know in June which mission is going to be chosen by NASA. And then I will leave you with these numbers of Cassini-Huygens, the number of miles. I guess they put that in miles somewhere. I don't know, but I think it's no, maybe not here. But okay, so you have the commands, the number of flybys, etc. Moons that have been discovered. 27 nations who have participated. Number of papers. This was last year when, well, in 2017. And the number of images that were, oh yeah, here I can see 5 billion miles since the launch. Okay, thank you very much.
So we thank you for this beautiful trip to Saturn and its moons, and we have some time for questions, comments.
At this slide, what is the price of this slide?
So that's a question I had. You know, a journalist called me close to the end of the Cassini mission and asked me, you know, what's the price? So the price is $4 billion for this mission. And so, but I didn't give that price first. I say, you know, there are 400 million people living in the US, and the Cassini mission have been around Saturn, you know, 20 years mission. So it's about 50 cents per year that each American person has given for this mission. What can you get for 50 cents per year? Well, you get the scientists who can give seminars. You can get the website, the JPL website, to see the, you know, the wonders of the Saturn system. You improve your knowledge about the interior of Saturn, the moons, the formation of those moons. So what price do you put to knowledge? You know, how much each citizen is going to give in order to improve the knowledge. And so she took that and she said, oh, okay, yeah, I haven't thought this way because, you know, $4 billion, that's a lot of money. I said, yes, it's a lot of money, but it's spread, and knowledge is something which is spread over everyone. She wrote the paper, and in the paper it was Le Monde, so, you know, it's a very well-known French paper. And instead of putting 50 cents per year, she put 50 cents per day. And so I called her and I said, no, it's not 50 cents per day, it's 50 cents per year. And she said, but you are sure? I said, yes, I'm sure. And I had to do the math, you know, to tell her that you take $4 billion and you divide by 400 million people and you divide by 20 years and then you get the 50 cents per year. But for her, it was so little money that she couldn't believe that for so little you can get so much.
So you were the planner of this mission. Were you satisfied with the results of this mission?
Oh yes, of course, but I was not the planner. I was just on one instrument, so I just planned observation of Titan, which was just great. You know, I miss that now because, as I said, we didn't know anything about Titan's surface. So every time I had a flyby, I had to decide which spot on Titan I was going to look at, and every time it was something new. And I had about, we had 160 flybys of Titan, so I had about one flyby every month, and every month it was new discoveries during about 13 years. So it, you know, what we got from this mission is much more than what we imagined we will be getting. You know, the Titan's surface, we didn't know that we were able to see it. The Enceladus activity, no clue about you know, this activity on Enceladus. The presence of oceans in the small moons, that was another thing. We get data about the effect of tidal dissipation, which are very important for exoplanets and for other formation of the solar system. You know, it exceeded what we thought we would be getting by this mission.
You mentioned also a riverbed, but you haven't seen any water there.
No water, just liquid hydrocarbons. We saw lakes, we have lakes. But I didn't see water running in the rivers. No fishing. Or in the lakes you can go fishing.
Another question. Comparing to your information from the lecture you have been for the last time, are there any news about the internal structure of Titan, especially in terms of the subsurface ocean? Or did you actually observe some sort of exchange between the subsurface ocean and surface?
Okay, so I guess last time I mentioned that there is argon-40 in Titan's atmosphere, and argon-40 comes from the decay of potassium-40, and potassium-40 is in the silicates, so it is inside Titan. So somehow we must find a way for exchange between the interior and the atmosphere. The same for methane, because methane, as I said, it has to come out. Maybe with the geology, we will find, you know, some features that will tell us that there is some exchanges. Some work we have done with Clara is also to look at what we call the high pressure ice layer. I don't know if you remember the presentation, but I guess I spoke about that, which is in between the ocean and the rock. And what we demonstrated is that actually you can still have exchange through this high pressure ice layer between the rock and the ocean. Now, between the ocean and the surface, I think we don't have yet a clear answer. But what we have done during my months here, looking at this, the effect of the class rate layer on the surface, it's very promising. So I don't have yet all the results, still ongoing work, but it's, yeah, it's quite exciting. But in terms of new things, well, we know the crust is about 80 kilometers, but when I say 80 kilometers, it can be 50 or 100 because we don't have a seismometer. By the way, on Dragonfly, there will be a seismometer. So if they choose Dragonfly, the mission to Titan, then we will get some information about the interior structure. The ocean, we don't know if the ocean is 10 kilometers or 300 kilometers. And we don't know about the high pressure ice layer. So we you know, there are still things that we don't understand.
Another question?
So I see that the mission has brought many, lots of discoveries about Saturn and its but are there also some discoveries which are generalizable in geology or even in physics?
Well, if for physics you think about, you know, the formation of planets in a stellar system, you know, with discoveries of exoplanets, for example, big question is how do you form a planet like Earth? Is there another place in the universe where you have another Earth? So we try to understand how you can form the Earth. And by looking at the formation of these small moons from the rings, or the dynamics of the rings, then you get some data about the formation of these bodies. You know, the tidal dissipation, for example, that I mentioned, it's something that we had no clue before Cassini. Well, we had some clue, but I think tidal dissipation in the planets and in the moons is a very important process to provide energy inside the planet, and that's something that is, you know, emphasized by what we are finding on Enceladus. So there is a lot of physics that you can apply to understand the formation and the evolution of the system, and this is the same laws of physics that then you can apply. You have the data on Saturn, and then if your model works for Saturn, or the moons of Saturn, then you can apply that to other places in the solar system, but also in other solar systems.
So perhaps one last short question. Yeah.
I read that Cassini is powered by nuclear fuel, plutonium, and when there was a flyby around Earth to get the gravity assist, I heard that there were some concerns that if it's going to collide with Earth, there will be many millions of people will die because of radiation. I would like to ask if future missions are in danger because of the movement to renewable energy that is kind of bad for the...
So first, the batteries, the nuclear batteries that we are using are small in terms of the total amount of power. We on Cassini, it's 700 watts that we had. You know, so it's not a lot of. It's not a generator. It's not a kilowatt, 10 kilowatt generator. It's very small. So when you look at, so they made the calculation. They looked at what happens if the rocket explodes at launch. You know, how much radiation do you get? And it's less than if you live during 1 year in a house on granite, you know, because granite has a lot of potassium, and so there is a lot of there is more radioactivity on granite than there is on other sediments. So they made those calculations in order to show that it's not a lot of radioactive elements. But I do remember, because it's one of the stories, you know, some people thought that it would be the end of the world, because it was 2000, you know, that we did the flyby of the Earth. It was 1999, the flyby of the Earth. So there were some people who thought that Cassini would get into, would hit the Earth, and it would be the end of the Earth. And I know one person who built a bunker in his garden just to be protected because Cassini was going to fly by the Earth. But I mean, NASA takes that very seriously in terms of these nuclear batteries. So Voyager had the same kind of batteries. The rovers on Mars, the large ones, have also this kind of batteries. That's how, in the movie The Martian, when he looks for some energy, that's the battery that we have on Curiosity. And what are the other? New Horizons had also nuclear batteries, but we try to avoid, well, actually the law is to use them if you can demonstrate that you cannot use other ways, solar panels, to go to a place. So, but we don't have much batteries left, actually. I think there are only 2 left right now. There is the ones for Mars 2020 next year, and then after that there will be 2 left after that. So it's yep. The short answer is yes. Then now I have a long answer because at JPL I work on this kind of problem. We work with the Department of Energy in the US in order to see whether we cannot use different kind of nuclear power. We're working on fission instead of radioactive decay. And I will stay here if some people have some questions. I can stay after my talk.
Yeah. So this invitation you can accept. So thank you very much again.
You're welcome. Thanks a lot.